So yeah, so I'm Dave Conkey, and we're going to be talking about the SGP4-XP algorithm. This is far less intriguing than JP's talk or Luke's or everybody else's. Nah, I don't know. You can judge for yourself. Yeah. So what is the SGP4-XP? So I think probably most people know what the SGP4 is, the simplified general perturbations propagator, version 4. I don't know whatever happened to version 2 and 3. But the SGP4-XP is an extended precision version of that. And since I don't have as cool graphics as Luke and others do, I do goofy ones. So, but I think it helps blur out some of the tedium of the slides. So, yeah, the XP4-XP expands on the propagator precision of the legacy SGP4, which is fairly coarse, and we'll talk about that more in a bit. But first, I'll give a little bit of background on me. I have a bachelor's degree in aerospace engineering from Virginia Tech. Started working at the C-130s at the Bell Bomber plant in Marietta, Georgia. That's where they build F-22s and C-130Js, which is kind of cool because it was neat to see how they actually, build things. But it was kind of a bummer to be a hotshot engineer coming out of school and having to work on a 50-year-old airplane. So I quickly moved over to AI Solutions and have been there for a long time. And I don't quote that date because people make fun of me every time I do for being old, which I am. Supported lots of missions over the years. Worked on EO1 initially, which was an awesome mission. Look it up if you don't know about it. Trim, Aqua Orbiter, the LEO regimes, GPS, NASA Care. I think Michael Wally just mentioned that a little bit in the last presentation. Worked on TDRS a little bit, other GEO missions, JVST, and other new space stuff. But with all that, most of the time I spent is been on as a software developer for FreeFlyer. So that kind of tells you how old I must be, or gives you an idea. I've had a good career, made a nice career, been lucky working with people that are really the best in the industry at AI Solutions. So as an individual who only has a bachelor's degree that is at the company, where most have master's stuff, I've learned from the best of the best, so it's been fun. That's my unapologetic no to AI and FreeFlyer. All right, to the details here. Terminology. I'll start with some terminology and I'll screw up some of the stuff along the way because I've been working through it for, like I said, lots of years. But we're talking about TLEs and the process of generating TLE. So TLE basically is generated via the SGP4 algorithm. And in the old days, NORAD used to do that. Nowadays, Space Force does that. Nowadays, they generate in different formats. One is so TLE, T-line element, just to be explicit about it. So that's the classical format you see there. The LMM is the new format, which is a part of the CCS, DS, ODM spec. Kind of not getting into all those acronyms. But it's kind of the new way to do it, and it's kind of somewhat loosely managed. Yeah, I won't get too much into that. The GP, I'll say GP a few times and SP a few times here. GP model is a general perturbations. That roughly, means it's an analytic model. SP is like an integrated model. So that little picture down the bottom there is a butcher table for RK integration. So if that's interesting anyway. So yeah, the classical SGP4 algorithm is is defined in Space Track Report number 3, and there's a link and a QR code, because QR codes are cool nowadays. I don't know what it means, but whatever. There have been multiple updates over the years. There's implementations in lots of different languages, in C# and Python, and probably Visual Basic and C++, definitely, whatever, I don't know. But the problem is that there's a lot of variations in those implementations. And FreeFlyer had its own native implementation up until version 7.7. I think this was mentioned a little bit earlier in one of the other presentations, but in FreeFlyer 7.7, we integrated the US Space Force implementation as as what FreeFlyer itself would use. But there's a kind of an inherent problem in the fact that you have different people implementing the same algorithm in potentially different ways. And so that's why the Space Force, and originally, I guess maybe it was JSPOC, I don't remember now exactly, but initially released the quote unquote official version of the algorithm. So yeah, so with FreeFlyer 7.7, we included this official, quote unquote, official version as the main propagation algorithm for using TLEs and that mean element set. But also included in that algorithm is the SGP4-XP, and that's really what we're talking about. So finally, let's get here. So at nods to NASA quote, faster, better, cheaper. The SGP4-XP, it's so these are some quotes from the release notes from the distribution for the algorithm coming from the Space Track from the Space Force. The new SGP4-XP is statistically equivalent to that of the SP. That's kind of an interesting quote. Yes, but it's slower than the legacy SGP4. And we'll talk about that a little bit more in a few more slides. But really what it has is improved lunar perturbation models. You can now also model AGOM and B-star at the same time. If those of you that don't know, AGOM is area times gamma over mass, which is just an SRP term. So we're talking about SRP and drag, but they're both non-conservative forces. So I'll hit on that again in a little bit. Updated gravity terms, I think it's WGS 96 now says 72, which I think the old SGP4 used 72. It has an improved drag model. So the legacy SGP4 had a static drag model, and the new one includes a variable flux that kind of trends towards the solar cycle. But I don't want to present myself as an expert on this, on the model's details itself. Check out the release notes, dig into whatever information you can get from them. I'm really just trying to cover some kind of initial analysis from using the algorithm that we've come across. Cheaper, well, yeah, so now it's, like I said, it comes with the ASH standards distribution that you can get from Space Track with any account you have there. So it's quote unquote free. Yeah, but it's not really free, right? Because you need a system that can generate these TLEs that can do fits using this algorithm. To date, last time I looked, the Space Force wasn't publishing SGP4-XP derived TLEs. Well, you can't generate them. Well, yeah, let's get in the next slide for that. But but really the bigger thing is the third bullet here. Is you also need a system that can read them and process them. So classically, TLEs have been used for. I mean, they're used for all kinds of things nowadays, and sometimes appropriately and inappropriately. But I think that kind of the main point of having them originally was that they would be used for ground systems to generate pointing schedules, and the error that are in the basic SGP4 derived TLE is okay. It's good enough for having a ground station figure out when it needs to start pointing from here to here to track a satellite. So, and that's been the traditional usage. But nowadays, some of those requirements are changing. I'll hit on that a little bit. But again, nobody, or Space Force at least, isn't generating these higher precision derived TLEs, but you can use FreeFlyer. Yay. So, so getting a little more technical detail here. The process that we're going to be generally going through here is taking an ephemeris that is considered to be a high fidelity ephemeris, probably derived from the high fidelity OD process, and then fit a set of mean Keplerian elements to that ephemeris and propagate them along to minimize whatever error is over the trajectory of the fit process. So in FreeFlyer, it's really as simple as kind of this snippet here. And so you load an awesome EFM from your OD process. You set the fit span. You set a spacecraft to use an SGP4 propagator. You set an a priori state. You do a fit. And this line here, line 17, as it is, and that actually will execute 3 iterations by default of a batch squares process to optimize a set of Keplerian elements to fit that trajectory, and then write out your awesome TLE. So if you want to do this with the SGP4-XP, that's a mouthful for me because I used to just say SGP4. All you really need to do is specify the ephemeris type. So just real quick on that front, they are using the ephemeris type field from the TLE to specify how the fit was performed. Traditionally, this is a value of 0. I've only ever seen a TLE published with a value of 0. There are other scenarios where people might use other values there, but anything published officially, I've only ever seen 0. 0 is, I think it implies using cosine mean motion, but now they're saying that they'll use 4 to specify that it uses this SGP4 algorithm. But also you get to now choose whether to estimate B star and or agon, again, the drag and the SRP terms. And you can choose one or the other, and I'll hit on that in a bit because, again, they're both non-conservative forces, so it's a little bit, in my experience, a little bit gray in how they've been, and how they alias each other. So, yeah, so for the results that were we will look over here. This is the approach that we're going to take. So we're going to take a reference premise, assume it's high fidelity OD solution, sample different states off the premise at different times. I think for this rough presentation here, we're taking about 300-second step sizes. And we'll use the FreeFlyer default tuning. Usually the default tuning works really well for an SGP4 fit because there's a lot of error in the model anyway. So this is not like a rigorous mathematical explanation of it, but I think of it like having a white noise bound, like here. So you get a point here, point here, point here. They're all pretty much the same. So having a lot of noise in that system, or a lot of error in the system, then allows you to have a tuning that's not necessarily super defined. But we'll also look at it. So we'll look at a few different ore types. The MIO, which is GPS-like, so circular. Monoi-like, so a 12-hour orbit, high eccentricity, and geo. And the primary way we're looking at this is to look at the range difference between what we consider to be the truth ephemeris and the reference ephemeris from the high fidelity OD to the propagate state of the SGP4, using the SGP4 and using the SGP4-XP. And this is kind of crude and coarse, and that's on purpose because I wanted to have it consider how out of the box, so to speak, things would work. But okay, so then we'll talk about tuning a little bit. So then maybe out of the box, but then with little tweaks. The TLA fit process, for those that don't know, it's really just a batch least squares fit. We talked about that in some previous presentations. I covered a lot of this in terms of the coarseness of the model and things like that. But the main bullet I want to hit here is that for an optimal solution with SGP4-XP, maybe we need to be better, and that's where, like, if I'm thinking this is a white noise distribution in the solution that you can get, maybe with SGP4-XP is more of a Gaussian type curve or something like that. And again, that's not at all rigorous. I'm just trying to give a concept of the idea. So if you're gonna try to get to the optimal with the curve there, then you need a little more tuning. And that's where, like, being able to tune V-star versus AGOM and managing how they alias each other, forces, how that plays into it. And as we'll see here shortly, that may be more important when you're dealing with LEOs. All right, so let's just some results finally. So this is a plot, 6-day fit span. You have what I'm showing here in the blue line. This is a propagation of the geo of a geospacecraft using SGP4, and a propagation using SGP4-XP after doing the fit. So there's 20 roughly. You got a 1 kilometer error using the SGP4, and you have roughly 100 meter error using the SGP4-XP. So moving on to the MEO case, this is a MEO in terms of 12-hour orbit, circular orbit, GPS-like, And here again, something much better. SGP4, the classical legacy, does better than the Geo case, probably because of less lunar perturbations, but the SGP4-XP is definitely a lot better, and let's say in the 50-meter range. So this is the Monaya type orbit, 12-hour orbit, highest centricity, maybe 0.8, I can't remember exactly, but you can see that actually neither algorithm does particularly great. This is an area where I think maybe tuning could improve the XP's performance, but again, I wanted to try to capture the out of the box behavior. Yeah, in short terms, you can see 12-hour, you can see structure over 12 hours here. And more or less comparable, maybe a little better over short flight spans. And Leo. So with Leo here, it basically is almost exactly the same. And in terms of overall performance, obviously the instructions are a little bit different. In terms of having a fit at a given accuracy level, we're still a kilometer level, roughly, I don't know. So it's not really offering any substantial benefit at this level. And again, I want to point out that I think that there's potential to improve that with additional tuning. So yeah, this is just kind of covering the statistics from that. I won't go into too much details, but I guess if you look at this column, second column, and fourth column here, and then compare these guys and these guys, you can see that Geo is definitely much better. Mio is definitely much better. Leo not so much. And the high centricity Mio not so much. But one of the, of course, one of the things that's supposed to be important about this is that the XP is supposed to be much faster than the SB. As it is, in the quote earlier, they said that, the quote from the release notes earlier, they said that the XP was slower than the legacy SGP4. In operations and practical usage, it's pretty close. This is so this is about showing the runtimes using FreeFlyer, and there are overheads in using FreeFlyer with this algorithm, but for the most part, numbers are pretty close. And I'm showing this here as a raw propagation versus an OD fit. And the OD fit that I'm using here is a 3 iteration of a batch least square. So there's additional overhead in the batch least squares process here as well. But for the most part, it's not overly burdensome, I would say. I would say it that way. So finally, the same thing I've said 3 times now. The Geo it seems to do much better. And Mio orbit like a GPS, it does good. And Mio orbit like a Monaya, which these days are pretty rare, I think. I don't know. It does better. But in Leo, it's about equivalent. So why do we think that might be the case? The drag model maybe still isn't great. The geopotential model maybe isn't great. Maybe we need to do more tuning. And I tend to believe it's more about the geopotential because over a relatively short, data span, you're not sampling drag variability all that much. I mean, it can obviously vary, but you're definitely sampling more of the geopotential model over in Leo orbit, even Mio with a high centricity. So my feeling is more about the geopotential, but more analysis to be done, so you kind of drill down into that. But the last point I really wanted to make here is that being a lot better in geo and MEO, it permits using an SGP4-XP fit to have uses in cases where you have a lot tighter mission requirements than what you would normally have had with other TLE fit missions. So that's all I have. If you have any questions, yeah, let's bring them on.
All right, thanks, Dave. Yeah, great presentations. Thanks for talking about this cool analysis that you did with something that we just implemented into FreeFlyer. We have a quick question from the audience. It's actually regarding your FreeFlyer script, and I'll be able to answer this real quickly. But are we seeing FreeFlyer in a dark mode here? If yes, what version of FreeFlyer would this be in? The answer is with FreeFlyer 7.6, you can use the plot styling utilities to make those plots any different type of color that you want with different color palettes. This script right here that Dave's showing, you're able to change your user preferences to customize those colors. So just the code portion of FreeFlyer would be in dark mode. The rest of the user interface would not.